Hello and welcome to the Geographic Calculator webinar for the month of December. Currently all attendees are in listen-only mode and you should be able to see our first slide on the screen. My name is Josie McKnight. I'm an application specialist for Blue Marble Geographics and I'm here with Sam Knight. He's the Director of Product Management.
Good afternoon, everyone. Today we're going to be talking about datum transformations throughout the Geographic Calculator. Josie's going to be joining me, helping me out with some questions. We're going to be trying to take questions live. There are quite a number of you signed on today, so we are going to try and do questions through the questions interface that will be found on the right-hand side of your screen. I do anticipate a number of questions today, and if you do have questions that we're not able to get to, or if you think of something after the fact, you can always find us at geohelp@bluemarblegeo.com, and that address is right at the bottom of your screen. So I think we're going to start today with a quick poll, just to find out what kind of an audience we've got with us here today. So we're going to ask you how long you've been using the Geographic Calculator. And you should see that poll coming up on your screen now. And we're always interested here. It helps us cater our presentation a little bit to the audience that we have. So it looks like we have a pretty heavy contingent of folks just getting started with us, and some more experienced users in there as well. I'm going to leave that open for just another few seconds, and looks like it's slowing down. So I'm going to go ahead and wrap that up, and let's take a look. So looks like just under 70% of us are just getting started with the application. That's great. Then a few in the 1 to 2 year range, a few more in the 3 to 10 year range. So we have a really good mix of folks with us today. And there are a couple of you in that 10 to 19 year range. So for those of you that are new to the calculator, just take a look at that. There is always something you can learn with this software. There's a lot to it, and there's a lot to the topic that we're going to be talking about today. Let's just pull that back off there. And let's get on to our next slide here. So today we're going to be talking about transformations. And you'll notice I didn't say datum transformations in there, because there are actually a number of different kinds of transformations that we can do. There are things that are more generally referred to as coordinate transformations as well. And datums aren't the only thing at play. The types of data that the stuff we're going to be talking about today applies to is everything. So where transformations take place is on every single interface in the Geographic Calculator. So the interfaces we're going to be looking at today are mostly, we're going to take a look at some examples on the interactive panel, just because it's a nice simple place to work. But this does apply everywhere throughout the Geographic Calculator. So first off, what is transformation? This is a question a lot of folks come to us with. We talk about having different types of coordinates. We have different units. We have datums. We're starting to get more and more vocabulary words in the industry as awareness, geodetic awareness increases. And one of the big ones here that's a little bit subtle sometimes is the difference between transformation and conversion. Transformation specifically changes your data in a way that conversion does not. And specifically, transformation degrades your data. It does not matter what kind of a transformation you are doing, but transformation, the parameters, the math that we do, is all empirically derived, meaning we figure out the relationships of these different models that we're transforming between. So what that does is it is the only step that is not mathematically pure, if you will. So a conversion is very commonly regarded as zero accuracy loss. A transformation is regarded as some level of accuracy loss, with the end game of a transformation being as little accuracy loss as we can possibly get. So the idea of a transformation here is to pick the best possible transformation for your data and get it as close to being a conversion that we can. So the calculator has a comprehensive set of different methods for transforming all different bits and pieces. So we're going to take a look at some methods of transformation. And I'm just going to put a few of these up here on screen. And these are all different vocabulary words you might run into in different pieces of software. You're definitely going to run into these in the Geographic Calculator. And there's different significance to picking some of these different models. And these aren't even all of the different types of transformations. These are just ones we bump into very frequently. So what we have are everything from your basic 3-parameter. People talk about having deltas. People say I've got some deltas for my x, y, z's. A lot of folks don't really think about what's going on in there. We have some standard notation you very often see. The parameters we refer to are changes in x, y, and z. We refer to those as either change or delta or shift, but that's described by the little d's that you see here ahead of the x, the y, and the z. Sometimes you'll see that listed as a little triangle just indicating change. Those are usually going to be expressed in something, a common linear unit, such as meters or feet, depending on where you are in the world, whatever your local survey standards are, your geodetic standards. All of these x's, the y's, and the z's that we see, they're different things that we're going to do to an xyz, but the xyz is very often sort of lost. We lose a lot of folks at the very first step when we start talking about xyz. XYZ to the everyday user very often simply refers to a surface position, but that's not at all the case here in talking about transformations. These methods that I've listed on screen here are mostly methods that are used for datum transformations specifically. The x's, the y's, and the z's that we're talking about are relative to the 3 axes. And I'm moving my mouse here along the screen. I'm hoping you can see my cursor on our screen share along the central axes that you'll see in the core of our cutaway model of the globe here. Those central axes are defined as our x, y, and z. So they're relative to the geocenter of our planet. And what we're doing is setting up a 3-dimensional Cartesian space with our planet at the center. So the axis that we use that comes from the geocenter up through the North Pole, down through the South Pole, that is our z-axis. That's sort of our theoretical axis of rotation, ignoring all the wobble in the planet. The x and the y-axis are our equatorial axes down here. So the x-axis comes from the geocenter out to the surface of the planet at the location wherever we put our prime meridian. And on example here, we're using Greenwich for terminology as our prime meridian, just for common language. Our y-axis is going to come out from the geocenter along the equator, 90 degrees offset. So typically, if Greenwich is our prime meridian, the y-axis that we're talking about in this 3D Cartesian plane is going to pop out at the surface somewhere in the Indian Ocean. There are these 3 axes that we're going to end up doing all this math through with our positions. Our position is up there as point P on the diagram. So you'll see point P, it's a little red dot here with P next to it. That is the position we're going to be relatively talking about. The point is described relative to the planet. The axes are sort of the most fundamental way that we have to describe the position of that point.
Sam, hey, we've got a question here from someone in the audience. It says the XYZ Cartesian system is also known as ECF, right?
Yes, that is correct. So there's a few terms for this type of Cartesian system. ECEF stands for Earth-centered, Earth-fixed. The Earth-fixed of that part basically just means that our x-axis is pinned to the equator, so the system rotates with the planet. Another term for that is simply 3D Cartesian. Some folks call it XYZ Cartesian, but there's a few ways to refer to that. So the point that we're talking about, we're going to be reducing all of our coordinates, whether they're latitudes and longitudes or projected coordinates. We're going to be reducing all of those into this 3D Cartesian system.
Okay, Sam, another question. Why does the position vector P not intersect the geometric center of the sphere?
Okay, now that's a good one. This is one of my favorite topics. On a ellipsoid shape, which is what we have with our Earth modeling, our ellipsoid shape, when we take that point at the surface and we trace what's called the normal line, so the line that would be perpendicular to the surface where you're standing on the surface at some theoretical spot, that line does not actually go to the geocenter on an ellipsoid. So that line you're going to see goes near the ellipsoid, but it's not actually going to go, or near the center of the ellipsoid, but it's not actually going to go to the center. That right there is one of the reasons that geodetic transformations are so tricky. Ellipsoid math is much, much more complicated than sphere-based math. So what we have are our point, we have all these axes that we're going to be talking about, and all of these different shifts that we have on screen here, the 3 parameter, the 7 parameter, 10 parameter, and so on. All of these different methods are ways that we're going to be figuring out how to move the geocenter of our model to the location of the geocenter of another model. So essentially what we're doing is taking our description of the location of that point P, and we're not actually moving the point. The point stays exactly the same. It's the description of the center of the planet that we're going to be locating. That's why we call this a datum shift. It's the datum that is actually going to be moving to a different location rather than our point. So all of these different methods we're going to bump into here. We've got 3, 7, 10. We have grid-based methods, multiple regression equations, polynomials. All of these are different kinds of math, and depending on the derivation they come with, they're going to come with different levels of accuracy.
So thanks for sharing that, Sam. Can you share with us which one is the best?
So the best is a very, very tricky question. All of these have the potential to be the best. It depends on the specific derivation. It depends on the quality of the survey control that goes into it, basically the rigorousness of the math that is done, and the chosen delivery mechanism. So it is entirely possible for a 3-parameter transformation to be superior to a 10-parameter transformation, or a 7-parameter, or a grid, depending on the size and the scope of the area that the data is being converted in. So that's a little bit about what we're going to be talking about here today. There's really sort of 3 main categories here that we're going to bump into, and we're going to be talking about fixed epoch transformations, which is what the majority of these are that we have on screen. We're going to be talking about time-based transformations, and we're also going to be talking about direct transformations between projected or Cartesian systems. So we're going to be taking a look at all of these. So just a quick example of what happens when we choose a different set of transformations. Just a quick example on screen here illustrating a common conversion that we do in this part of the world from our local system called NAD27, and I expect for any of you that are joining us from the States today, NAD27 should be a familiar animal to you, to WGS84. The sort of common world model, the GPS-based model these days. And I've got a couple methods listed out underneath that text there. You'll see NADCON, MRE, which is multiple regression equations, Canadian NTV2, and a couple of Molodinsky shifts involved there as well, and some accuracies that go along with those. Now, on our picture here, you'll see there is a green dot, and the green dot in the center of this, this is actually an oval running track. This is happens to be the running track here at a local high school in our nearby area. And the green dot is the position of the throw line of the javelin for the track and field events. And so they provide a very convenient shape for us to model this out in our local area. Now, the positions that we have here on screen come from two different coordinate systems. Our base raster image here is referenced in WGS84, and the position we started with was a NAD27 point to place that on the screen. So the location of our green dot began as a NAD27 latitude-longitude. To get that on the map, we had to transform it to WGS84. If we didn't do that, it would actually not even appear within the center of that oval. It would be a couple hundred meters away. So what we have here, all the red dots, and actually the green dot as well, all of those dots represent different transformation parameters that are chosen. So all of these dots are actually NAD27, the same position there at the start of our throw line. They began at NAD27 and we transformed them to WGS84. So this is where the significance of the methods we pick come in. The green dot on screen there is represented for the NADCON conversion. So in this case, this is a grid-based conversion. It involves a data table lookup. So essentially, if anybody remembers something like trig in high school math, we're looking up in a lookup table, a geographic lookup table, a small local offset to apply this transformation. This is actually the national transformation for here in the United States. Other parts of the world have similar things. For us, it is the most accurate, and it delivers about a 15 centimeter level of accuracy. The next dot down is our MRE transformation, and again, that's multiple regression equation. This particular set of transformations comes to us from an old military publication. So the U.S. military was responsible for a lot of transformation parameters that are out there in the world. In this case, it's supposed to be accurate to about 3 meters, and in this case, it actually gets us within a little less than that, so probably about somewhere around 2 meters, I think that is. Then the next dot, a little bit farther away, this is where it starts getting a little more interesting. The Canadian NTV2 grid. So this is the national transformation for Canada for the same combination of systems. This actually falls 3 meters away from where we intend to be. And in Canada, if we were doing this on a different coordinate, that would be much, much closer. In Canada, this is accurate to about 7 or 8 centimeters. But we are in the location of Maine here, so we're a few hundred miles away from Canada, so their data tables don't cover our area. So it is possible to complete this transformation. It's just that table doesn't have particularly high-quality data for this region. And then a couple farther away there, a couple of Molodensky 3-parameter methods. So one delivering 13-meter accuracy, the other 14.5-meter accuracy. And those are both coming from sources, one generalizing a transformation for the entire eastern half of the U.S., and the other being a very, very generalized transformation covering the entire continental U.S. So by the time we go from our NADCON transformation out to our continental U.S. 3-parameter method, we're talking about a difference here in 14.5 meters of accuracy delivered on the ground. And for those of us not used to working in meters, 14.5 meters is about 50 feet on the ground. So we're talking about a pretty good distance. And on the bottom of the image here, or rather the bottom of our collection of dots, you'll notice there are some that are getting farther away. And just for reference, these lines on our javelin field, those are actually 5 meters apart. So by the time we go from our start point out here to this one, I think that's either 15 or 20 meters out, and then 25, 30, 35. We're getting pretty far away by the time we get out to that last dot. All of these dots are actually appropriate transformations from NAD27 to WGS84. They just represent different choices of the exact parameters that we're looking at. So today, what we're going to be talking about in the software, if we can hop out of here, we're going to climb over into the Geographic Calculator. We're going to be looking at how to make sense of these transformations. So first, we're going to be looking at just a regular old transformation from, in this case, NAD27 to NAD83, the North American datum of 1927 to the North American datum of 1983. Seems simple enough, and we're going to take a look at just how complicated it actually is. Now, here on the interactive job, we've got our coordinate systems already set up, and in this case, my output system is a UTM zone. For simplicity, I'm actually going to change this back to just our base NAD83 coordinate system. So I'm going to do a simpler lat-long example than I had set up. So I'm going to take a look down under my geodetic systems. I'm going to get into North America, and I'm going to find NAD83. So 2 continent-wide systems here. I have a point, 44 north, 70 degrees west. Anybody that's seen our webinars before, I'm sure you're familiar with that point at this point. So that's somewhere off in the woods nearby where we are here in Maine. And we're going to be transforming this point over to NAD83. So the point is not going to be moving. It's just our coordinate description of that point. So under the hood, what's going to happen once we pick a transformation is we're going to take that latitude and longitude, we're going to do a little bit of linear algebra to it, and we're going to turn that into an Earth-centered, Earth-fixed, or a 3D Cartesian linear description of that point in those 3 directions, the x, the y, and the z direction, on the axes of the planet. We're going to apply a shift to basically the origin of that system. So we're going to apply some sort of a shift to that, and then once we're in our second Cartesian system, we're going to do the first math we did, that little bit of linear algebra, and up on the other side of the screen is going to pop out our latitude longitude coordinate. So we're actually doing a couple things under the hood here to do the transformation. When we're actually doing this in the application, it's as simple as putting in your input point, picking your systems for input and output, and double-clicking on that box in the center to grab your transformation. So by the time we do this, we've already done about 4 things underneath the covers in the application, and we're delivering a cut-down list of all of the possible transformations to get between NAD27 and NAD83. So we have a nice short little list here for our combination of coordinate systems, and you'll see one of them is a direct transformation, and the other set of 3 are actually doing 2 transformations. So you'll see one goes straight NAD27 to NAD83, and the others combine a stop on WGS84 in the middle. So it's going to go NAD27 to WGS84, and then it's going to go from WGS84 down to NAD83. So this combination of 4 is, first off, it's reduced by where on the planet you happen to be working. And that choice, the where on the planet you're working, is dictated by the data that you supply to whatever interface you're working on. So here we're on the interactive conversions. And if this were on the point database conversions, on the vector data conversions, raster, anything else, by loading in your data, whatever that data file is going to be, by loading in that data file, that's going to give us the means of figuring out where we are in the world, where that data lives. The area of use is defined, and you'll see on this dialog, you'll see the area of use for the transformations listed. So what we're looking at here are 4 different ways to connect the dots between these 2 systems. The area of use, if we click on any of these, you'll see the map view is going to change a little bit depending on which transformation set we've actually picked. We have the area of use. So first of all, we need to be looking at a list of geographically appropriate ways to get between those 2 systems. Secondarily, we need to be looking at the accuracies of these lists. So all of these transformations apply for the same area. They all apply around that point. We show on the map below the map of the area of intended use for those, just to give you a good idea. Sometimes it's a good little sanity check on where exactly you are in the world, if you're working in a part of the world you're not necessarily familiar with. And then we take a look at the accuracy. And the accuracy, you'll see a couple of numbers here listed for each of those that are double transformations. So you'll see this first one is 4 meters and then 5 meters. And our first one that is only a single transformation is accurate to 0.15 meters, so 15 centimeters. Now, the accuracy is a very, very important part of this choice. And what does that accuracy mean? We talk about losing accuracy when we do a transformation. And so do we want the smallest or do we want the highest on these? And the whole point of the accuracy is that it is telling you exactly what the maximum error that could be introduced by using that particular transformation within the defined area of use. If you apply any of these outside the area of use, things can definitely go pretty crazy and you're going to have much larger errors coming into your data. But the accuracy is basically the maximum error you might be introducing within that area of use. So the ones that have the double accuracies, basically they're indicating that the first transformation, in this case going from NAD27 to WGS84, might introduce a possible 4 meters of error, and then the second transformation on that could introduce 5 meters of error. It's not necessarily cumulative. Some of them could be cumulative, so you could introduce as much as 9 meters of error in there, or you might not. But having both of those stated there is a very important thing to that choice. I see a couple questions coming in here about recording of the webinar. We are recording this session. You'll be able to download it right off of our webinar page once we have the recording cleaned up and posted. We put these all up in YouTube once we've completed the sessions. So back to that choice. Here we have a list of 4 possible ways to make that transformation. So ideally, we're looking for a transformation that surrounds the area that we're working in, and in this case we just have a single point, so that's pretty easy to find. And secondarily, we want the one with the smallest numbers in the accuracy column. So in this case, we're going to be steered towards this very first one in the list, and that's because we actually sort these by the accuracy.
Sam, will a single transformation always produce the best accuracy?
That's a great question, and not necessarily true. There are a lot of transformations that you might actually see in the database that have very, very small accuracies, or meaning very, very small errors that would be introduced. Some approach 0, such as the NADCON method that we're seeing there on the very top. It's possible to have transformations that are combinations of ones that are wildly different. You might have a double combination here of one that is 15 centimeters accurate and one that is 20 meters accurate. There's any number of possibilities. But the idea is that what you're looking at is essentially the smallest sets together. And I see a couple of more questions coming in. The questions are firing in here pretty quick. We're trying to answer them in line as we go, as best we can. Questions on, do you always want the best accuracy? And one question on the sort order. Kelly's calling me out here on 4 and 5 meters being higher in the list. I'll take that one first. The sorting is not perfect. We sort out the lowest accuracy in the single transformations first, and then the double transformations we're not able to sort those quite as well yet, specifically because they are combined together. So the double accuracies don't sort quite as friendly as the single transformations, and that's something we're working on in the interface. For the combinations where we need maybe something that is not the best accuracy, I'm going to save that one for just a minute as we start looking at some of the parameters of these. So what we're going to do is I'm going to right-click on that first transformation, and I'm going to say, let's view that transformation. This is going to pop open the definition of that transformation. Each of the transformations we have a definition panel something like this. The parameters are going to look very different from each other depending on that method. So in this case, our method is going to be a NADCON transformation. So this is our national transformation here in the US. The parameters for this are simply the lookup files that we have. So in this case, it's 2 data files, one for our longitude offsets, one for our latitude offsets. Those are combined and put together into this single transformation. Surveyors are required to use this method for this particular combination. Those files there tell you exactly what the data table is, and that's important to match up in different software packages. On the identification panel, this is going to give you a little bit more information, and it's actually going to give you the means of further lookup on the parameters that you've got. Now, the identification panel starts off with a simple thing like the name. The name, in most cases, is going to come to us from the epsg database, and we're going to take a look at that in just a second. The remarks from that are going to very often come from the epsg database, and sometimes the remarks will come from some alternate publication if it is not actually an epsg definition. On this definition, you'll see this is an epsg only definition. This is basically the main database that identifies this particular parameter set. As most of our transformations actually have epsg codes, a good place to take a look at those is directly on the epsg registry itself. So what I'm going to do here is bring open a browser window. We're going to take a look at that entry on the epsg itself. This is basically the next step of branching out to find more about a particular transformation set. So I got here by simply going to epsg-registry.org. That is a free and public website. Anybody can go there and look things up. There's no limitation to use of it. It's a completely free service. It is a service provided by the International Association of Oil and Gas Producers, known for short as the IOGP. And it's essentially a very comprehensive data source of coordinate parameters, transformation parameters, all those sorts of things. I looked this up by code. You'll see there's two ways to search. You can either do a simple text search or retrieve by code. And in this case, I got my code from our definition panel. I said, let's look up code 1241. That brings me to a list of things that match that code. I found the one that is the coordinate transformation I'm looking for, and here it lists all of its full parameters, complete with the similar information to the source and target systems, the files that are involved in that method. And then most notably here for lookup, sometimes you need a little extra information. And so we can go to the remarks over here. Has pretty much the same information that you'll have in the remarks in the Geographic Calculator, but it also has some extra things like the scope of the data, and that very often will give you more clarifying information about the accuracy of those. And in this case, it's telling us that the accuracy for this transformation is that 15 centimeters in onshore areas, but then it clarifies to say 5 meters in nearshore, and then questionable accuracy offshore. So this is a system that is used in those nearshore and offshore areas as well, such as the Gulf of Mexico, and it actually has somewhat variable accuracy as it gets off of the mainland. Then it goes on to tell us exactly where this parameter set came from. So this is creation of the U.S. Coast and Geodetic Survey, otherwise known as the NGS here in the United States. You can actually get into change logs on, so if the parameters have been altered over the years in the database. Full comprehensive information. Over there on the left, you'll see that accuracy again, but this is almost as much information as you can get around a particular transformation. So anything you see in our database with an epsg code attached to it, you can look that up and get even more information about where that came from. So with all of those, we have our list of 4 different transformations here that we're going to be choosing from. In this case, it's a somewhat obvious choice that I want this one that is 15 centimeters accurate rather than these others that are a little bit fuzzier in their accuracy. So I'm going to select that one. I'm going to say OK. I'm going to first take a look at one of these others just for comparison purposes. Normally you might check out a few of these to make sure that the one you're picking is the best one for your purpose. I'm going to view that transformation. And in this case, we have double transformation, so it actually shows both of those inside the concatenated transformation, which is what those the 2 transformations together are referred to as a concatenated transformation. I can select either of the individuals and bring up their information. And in this case, this is a combination of the CONUS tables from the NADCON method, but then also you'll notice a zero shift. And a zero shift is one of those cases where you might actually be picking something that has a sort of an odd accuracy for it. You'll see in this case those 4 and 5 meter statements on the accuracy of these are assuming that a couple of models are similar to each other, or what's known as coincident. So a zero transformation is not necessarily a terrible thing for some parts of the world. Sometimes the accuracy of those is stated slightly lower because they are simply assuming that two models are equal. And in this case, it's NAD83 and WGS84 are stated as being equal at that 4 to 5 meter level. So different combinations are going to produce entirely different accuracies. They're going to be based on entirely different collections of data as well. So let's go ahead and take that first one. We're going to come back to our interface. And at this point, assuming if we've had all of the formatting, everything taken care of for us in our job related to whatever the rest of our data is, we can go ahead and hit calculate. And we'll see the output data comes back. It's going to be a little bit different than the input data. That's the part we were talking about before, about the data actually changing from start to finish. So the point appears to have changed, but it is not the location of that point that has changed. The point is in the same spot. It's simply our description of the point that has changed. So that's an example of what we call a fixed epoch transformation. I'm going to complicate this by talking about what a not fixed epoch transformation is, a time-based transformation. So here we have a couple of models. These are our older models before time-based transformations really came into play. They are assumed at certain epochs. Our NAD83 here, you'll notice that on our horizontal datum, NAD83 is tagged as 1986 in parentheses. What I'm going to do is pop open our output system here, and we're going to take a look at some other models that you're going to see available here in the database. And so specifically, I'm going to drill down under the United States folder within the North America folder that our base NAD83 comes from. And we're going to see a number of different versions of NAD83. We're going to see NAD83 2011, HARN, HARN. Another term for HARN is HPGN. Some folks know it by that term. There's also NSRS 2007. And periodically, folks will ask about another model. And I see a couple folks asking about it in our questions list here, asking about a model called NAD83 CORS 96. That's CORS 96. With various epochs that further, for some folks, it just further confuses which one they should be picking. And for other folks, those epochs get to be very, very important for clarity. So these are some of the other systems that we have in here that are specific mostly to the US here. If we take a look down under the world folder, you'll see a number of other systems that are going to get involved here. ITRFs are a big one, the IGS systems as well. And since we're talking about all these different systems, one of the things that comes into play is you'll see there are two versions of each of these systems. So there are actually two 2011 NAD83s, there are two HARN NAD83s, and two NSRS 2007 NAD83s. If you take a look over at the right side of the screen there, you'll see dimensions, 2 versus 3. Those are indicating that we have some of these systems are two-dimensional systems and some of these are three-dimensional systems. That essentially comes down to an academic difference between these two. I'm going to generalize, and I'm probably going to maybe ruffle some feathers here if we have some geodesists on the line today. But for most folks in the everyday positioning world, there's not going to be a lot of difference between whether you choose those 2 or 3-dimensional systems. Where it gets most twitchy, I'll say, is when we start getting down at the very fine levels of accuracy and we start talking about vertical transformations. And moving between not just the side-to-side positions of our datums on the surface of the ellipsoid, but when we start playing around with the up and down of those transformations as well. It goes into how we actually reference the system. If we have a 3-dimensional system, that means we're actually operating on all 3 dimensions with our latitude-longitude system, the base geodetic system. The 2 dimensions are we just worry about the side-to-side part of that, and we let another piece of the coordinate system that we're going to add on to it handle the vertical for us. For most folks, I'm going to generalize and say that's an academic difference. You're not going to see significant behavior difference in the software if you pick one or the other of those. So what we're going to do here is take a look under the HTDP folder. And HTDP is sort of the main collection of our time-based coordinate systems. This is changing somewhat as more time-based transformations come along. HTDP is one way of doing time-based coordinate systems. And we're going to see how some of this has changed in newer versions of the software.
Sam, I have a question. Do I have to turn this on in Calculator?
Okay, the turning it on in the calculator, that's a question that's going to be asked by somebody who's been with us a little bit longer. The turning on the time-based transformations is something that existed for specifically the HTDP folder. HTDP itself is essentially an American transformation for the North American plates, basically, because when we start talking about time-based transformations, we're talking about plate tectonics and where those plates are moving around throughout the years. HTDP was the first way that we implemented for that, and back in the first implementations, it was actually a user preference. You had to turn it on in order to be able to see those. Now it is on by default, simply for time-based transformation. So there is still a preference setting, but it is on by default. So you don't have to turn it on, but if you're somebody that doesn't ever have to worry about the time aspect of your coordinates, you can turn it off. And the toggle for that, we're going to see right on the main coordinate system controls there. The toggle is actually going to control the presence or absence of these date fields. They're, again, on by default, and we're going to see those in action when we pick. I'm going to move over to a different example job here with a couple of time-sensitive coordinate systems. We have the same point we're talking about, but now we have 2 time-sensitive coordinates involved, meaning they have temporal shifts that we can apply to them. In this case, WGS84 with this G1150 tag. A lot of folks may not be familiar with the fact that there are actually multiple WGS84s out there. A lot of folks are comfortable just simply saying WGS84, that's the model, there's only one. We're just going to pop this open in our browser here, and you'll notice there are actually 3 tagged versions of WGS84 and then the original. The later tagged versions with the little G codes at the end there, those G codes stand for the number of weeks in GPS time since what's known as the GPS 0 day, essentially the day GPS went live, which is really coincident with WGS84. WGS84 was born out of GPS, and so those G codes are essentially updates for realization of the model. Now, for anybody that's interested, particularly in some of these, the WGS84s, the ITRFs, and the various NAT83s, including one we haven't seen yet, Cores 96. I'm going to talk about that in just a second. If you're interested in any of these, and you are also working on the North American plates, meaning your data is actually on the North American coverage, you can use what's called horizontal time-dependent positioning. For those of you who are working with systems other than what you'll see in the HTTP folder, and also in locations around the world that are not on the North American tectonic plates, there's another method in there called a 14-parameter transformation. And the 14-parameter transformation is another time-based transformation that's actually built around a 7-parameter datum shift, a more common mathematical transformation. So we're going to talk about this sort of two different ways. One is the HTTP way, and one is the 14-parameter transformation way. They both work the same. That's the good news. What we're going to take a look at here is what happens when we set up a transformation from one of these time-sensitive systems to another time-sensitive system. When I go to double-click in our center box there to pick the datum transformation, you'll see where we normally have our list of categories of transformations, we see only one category called time-dependent transformations for this particular combination. And then you'll see a blue listing in there. And this blue indicates that this is not something that is fixed in the data source. It is coming, in this case, from the external HTTP converter. So we don't actually have set parameters for this. It's a little bit like a grid-based transformation, but this is essentially coming out of this software called HTTP that is published by the NGS here in the States. It is really a black box system. We hand coordinates into it, supply the dates, and inside it actually does three things to the data. It applies a frame shift from one reference frame to another, and it does two temporal shifts, depending on the combinations of epochs that we've supplied for it. When we select that, this is going to, it shows you the dates, and the dates really give you everything about that point. So you'll see those dates. I'm just going to back up a step here before we do this. On the coordinate system controls, we've got the reference frame that we're talking about, so NAT83 NSRS and WGS84 G1150, and then we have these date boxes underneath. Those date boxes are really, they're a piece of the coordinate system definition. They don't tell you necessarily where your data is, but they give you the when of your data. So in this case, if we're talking about a time-sensitive transformation, by changing the dates, we're going to get different results. And that's modeling where those relative positions are as the tectonic plates are scooting around and moving all of our survey control benchmarks with them. So when we select those dates in there, we pick our transformation, you'll see the date becomes a piece of that transformation. And when we pick the method, in the center there, it's just simply going to tell us those dates again. It's going to say it's using the HTTP converter to do that. And then when we finish off our calculation, it's still just a regular old number, but that number is going to change depending on what year we put in there. So I'm going to just take this back to, let's say, we had going from 2011 there. Let's just take this back to the 1950s. You'll see when we change that data, blanks out the transformation since that date no longer applies. We can pick our transformation, and what's going to happen over here, watch our output coordinates change. They're going to change to a very slightly different position, modeling the tectonic drift. You'll notice that changed a very, very, very small bit. We're not talking about massive shifts here between these frames. We're talking about very, very subtle modeling. We're splitting the centimeters down here, and in some cases we're worrying about that last millimeter of position. This is something that is more and more common. A lot of folks with very high precision GPS systems are starting to ask about this more and more. Particularly here in the States, folks are talking about all these different NAT83 epochs. We're talking about some of those different frames, and they're changing all the time. So the one I've mentioned a couple times, Cores 96, Cores 96, if you go to the NGS homepage, they have a very simple online calculator for HTTP converters. Does single points, essentially. Cores 96, you'll find a little note in there that all of the NAT83 plates are, so NSRS 2007, the original NAT83, 2011, and so on, Cores 96 included. So all of those are plate fixed. So in the HTTP kit, those actually all use the same thing. We have not had NAT83 Cores 96 defined in our own database for a long time. Because it wasn't in the epsg database. Didn't have a standardized entry for that. That is actually changing with this next release of the calculator that's coming out. I just added Cores 96 to the database just a couple of days ago, preparing it for release. But if you are using any of the NAT83s, you can essentially pick the same thing. So you can say NSRS 2007 for your coordinate system right now to get the same data as if you picked Cores 96 in there. The date is essentially the primary defining factor for any of those NAT83s. And I saw a question come in about this specifically. We're going to follow up. We got your email about Cores 96. I'm going to send you a longer version of this answer, more specific to your scenario. But all of these transformations that we've been talking about, every single transformation we have, can be applied to any of the data types that we have in here, and they can also be done in a batch operation. So this is just simply the under the covers part of how this all works. The date ranges themselves that we see here on the transformations, they're a little bit open-ended. What we're talking about are sort of tectonic epochs in here. So you won't see massive jumps for the most part. These are pretty much down to, they're specified by fractions of a year, but really you're not going to see much of a change in your data until you start going at least several years, just visibly to show up with a change. The date ranges go back to the early 1900s, and I forget off the top of my head exactly how far off into the future those go, but it all basically comes right from the HTTP model. So you can't punch in a date that falls outside the ranges that are specified. For the 14 parameter transformations, you'll see that is actually a little bit different. You can apply models in there that apply to any epoch. And what I'm going to do is hop up into our data source menu to take a very quick look at the 14 parameter transformations before we move on. They function pretty much the same way. We just simply pick the dates in there, and we will see some of these are mixed right in. So the 14 parameter transformations, they are what are called parametric transformations. They simply are a set of math parameters that we apply in the center. Doesn't use any sort of external kit, and so we can actually crack these open and view the parameters of those shifts. So in this case, you'll see the rotations, the scale factors, the shifts that are in there. And on those, they all have changes over time. Basically, a change per year is how those work. Those all match up to things like the epsg database for where they apply. I just happen to pick one that's not. But you will actually see that in there as a time-dependent Helmert, so commonly known as a 14 parameter transformation. Got just a quick example of that. You'll see here's one from those ITRF systems to GDA94. If anybody's watching from Australia, GDA94 is one of the most common that has those 14 parameter transformations. We're running a little short on time, so I'm just going to skip right past this one and wrap it up with some vector transformations. Vertical transformations. So let's hop over here to a vertical transformation job that I have saved. So far, everything we've talked about has been what's known as a horizontal transformation and we've talked about the two different kinds of horizontal transformations, either a fixed epoch, meaning it's like a snapshot of one epoch, 1 year to one other date for those transformations. We have fixed epoch transformations, we have time-based transformations. They're both horizontal, so we're essentially worrying about the side-to-side positioning of our coordinates rather than the up and down of our coordinates. For vertical transformations, we start bringing in some extra vocabulary. We start talking about geoids, we start talking about undulations. Mostly we're talking about grid files or local offsets, things like that. You'll notice on our coordinate systems here, I've got the same horizontal coordinate system on input and output. My vertical is actually an extension of that coordinate system that we add right on to the bottom of that, so the vertical box at the bottom. So in this case, I have two vertical systems for input and output. I have EGM 2008, so Earth Geopotential Model of 2008, and I have the North American Vertical, sorry folks, tripping on my own tongue here. We have the North American Vertical Datum of 1988, the National Vertical Datum for the United States. And those are each represented by offsets from the ellipsoid. And those offsets are known as geoid models. So coordinate transformation around the ups and the downs is very similar in process to a lookup-based horizontal transformation. These all depend on external data files that we need on those machines. So I'm going to double-click here to activate our coordinate system model. And in this case, I've got a lot of stuff in red. And this is going to be what you're going to see when you do this for the very first time on your installation of the calculator. Now I'm working on a fresh install here myself. I just reinstalled this, so I'd have a nice clean setup for today's session. So all of my geoids are actually missing in here. When the grid files for these are missing, what you're going to see is the entries are all going to be flagged in red. And you'll see this little exclamation point off the front of there that's going to light up. And that simply indicates that you don't have the requisite grid files installed for this model. So to get these, you can right-click on any of those and say Download Missing Files. It's a very, very simple thing. Just takes a little while to download some of those. The EGM 2008 grids in particular are some of our largest, clocking in at 250 megabytes for the 2.5 minute grid, about a gigabyte for the 1 minute grid. Very large files. The US geoid models, all of the different years that you'll see there, those US geoid models are all, I believe, less than 50 megabytes, much faster download for those. With all of these, same thing applies. You can view the transformations, and in this case, we're looking at two transformations stacked back to back, just like our horizontals. So they have a source transformation coming from WGS84 to target of WGS84, and it's going to connect the dots there with our two vertical systems, stacking up those geoid transformations together. Vertical systems do actually have accuracies, and in this release here you're going to see that those accuracies are unrated, and that means that we have not yet been able to find a good source to put something in there. And so when you see the dashes in the accuracy rating, that simply means that at this point it is undetermined, and we will be filling those in there. But for the most part, geoid models are typically going to be national models, so they're going to be published by some government. There are some folks out there who can actually generate their own transformations, and we are supporting the ability to do that in the next release of the calculator. Folks are going to be able to create their own geoid models. Typically, we're going to be looking at the surveyors in the crowd for that type of a function. But through a combination of using our other main software package here called Global Mapper, That is got some very powerful gridding tools in it. Through a combination of Global Mapper's gridding tools, you're going to be able to create your own geoid transformations. And this is something that is very, very new, very cutting edge. It's really going to help power a lot of the new 3D work that is coming on all the time in the forms of LiDAR data and things like that. Mostly at this point, the addition of custom transformations for vertical models is fairly limited. Honestly, it's something that not a lot of folks have done over the years. It's very tricky to create this type of data. So these models are typically governmental publications. Some governments around the world have chosen matching standards to others. And if they have used a standard that we already have, such as the US geoid models or the EGM models, it is actually possible to implement custom geoid transformations. It's going to be much, much easier in our next release. So I hope I answered a couple of questions that folks have asked about those geoids. In general, to find the much more comprehensive accuracy information. Accuracy for the vertical models is fairly difficult to sum up with one little number anyway. The best place to go for those is to view the transformations, take a look at any of the identification information for those that might be there, EPSG codes, cross-reference those against things like the EPSG, find the governmental website. It's typically going to be some survey authority, and that will give you much, much more comprehensive accuracy information for the ups and the downs. On some of these, there are different types of transformations, and so I'm bringing up a different combination here. This is a combination of the North American vertical datum of 1988 to MLLW depth. And for those of you not familiar with tide-based models, that is mean lower low water depths. Those tide-based models are where things start getting a little bit extra, I'm just going to say it's extra funky in vertical transformations. Most vertical geoids are models of mean sea level. There are also tide-based models, and that essentially just moves the zero surface either up or down, depending on if we're talking about high water or low water marks. So in this case, we'll see some extra pieces. And if we go to pick our transformations, you'll notice that we start tagging these as tidal models. If we get into the parameters of these, you'll see they are grid-based, much like all of the various transformations are, but they don't go to the same zero, which is an important thing to note on any of these that are going to be tagged as a tidal model of the transformations. The vertical models apply just like the horizontal models. You really do need to use it's not as easy to sort of determine which model is the best for a given area. Typically, the places where we're going to see different years for the geoids, you're typically going to want to be working with the latest geoids that are available. So the way things work here in the US is we have every few years there's an updated geoid model that's rolled out, and each time a new geoid model is rolled out, the survey standards increment up to that model. So our current standard here in the States, to the best of my knowledge, is we're still using the 2012 geoid, and there's going to be new ones rolling out. Canada just rolled out an updated geoid model for the 2013 model for specifically the Canadian regions, very similar to the US geoid models. That's going to be fully implemented in our next release of the calculator. But for each of these places, the geoid models will typically simply work for an area or not. The latest model is very often your best practice is to be working with the latest model, so you're matching up with all of the survey standards for an area. If you do have any particular questions about setting up geoids, if you're not familiar with working with those, we very commonly would recommend that you contact our support team for specific guidance. Looks like I'm running out of time here, so I think I'm gonna just take a quick scan through some of our questions, and if I can grab a couple of questions from our list, we'll take those, and we'll wrap it up here with some questions.
Okay, Sam. Do time-dependent transformations suit Canada?
The time-dependent transformations suiting Canada, I think you're probably asking specifically about the HTTP ones I mentioned for North America. HTTP does cover actually all of the North American plates, so you can use that. To my understanding, I am used to working in the U.S. with it. I believe it does extend to Canada as well. One thing I didn't mention about the non-United States areas is the time-dependent positioning kit, the HTTP stuff. It can actually be used for reference frame changes, non-epoch changes in there. So if you supply the same epoch date for both the input and the output, you can actually use it off of the North American plates. That it is a partially a global model for those, but I do believe, and I hope someone will please correct me if I'm wrong, I do believe that extends up into Canada and also down into Mexico as it goes offshore a bit as well, covering some of the Pacific plates that are out there. Let's see here. Do we have anything else in there, Josie?
Let's see. Would you ever use an accuracy that is not the best?
Okay, I meant to take that one a little bit earlier. I think I wandered off without actually answering your question after telling you I was going to answer your question. There are times when you would use an accuracy that is not the best. There are cases where the rated accuracy in the epsg is a little overly vague for some of them, so it may look like it's a looser model than it appears to be. There may be cases where you would encounter business rules. And I've seen this happen for folks working offshore in parts of the planet that folks don't usually get to, where a business rule has been set up that they standardize on one particular transformation. It may be a relatively unknown part of the world, and so the accuracy is typically, if systems are a little bit unknown in the references about those, they will have overly loose ratings on them, so they may actually be higher accuracy. Folks in the military actually very, very commonly use transformations that are simply less accurate, but they are repeatable with very low-tech tools. A lot of folks usually chuckle at that one, but there's good reasons for that. The ability to reproduce data by hand in the field, if absolutely necessary. If you're depending on a grid-based transformation, you absolutely have to have some data table lookup to be able to reproduce a transformation by hand in the field. You can really easily do that with a 3-parameter atom transformation, and you're not going to do that so well if you've got to start adding parameters like 7 parameters, 10 parameters. You're certainly not going to be using a NADCON CONUS table for lookup. So there are a number of cases where you would not use the best, but it's typically going to be involved with business rules. Any folks that are listening today from a large exploration company, anything natural resources based, planet-wide, you're very commonly going to have a geodesist on staff that will have some sort of guidance setting those business rules within the company. If you don't know if you have someone like that on staff, start asking around. Start asking your GIS department managers. If you have teams that are in the survey teams that are in charge of those things, they might be the geodetic authorities for your company. It's always worth asking around to make sure that you're doing all of the the best that you can within your own organization. So let's see.
Okay. Hey Sam, can you transform line or polygon data?
Okay. Yep. That's a good basic one. We did look today at simply latitude and longitude coordinate positionings, but all of the transformations that we've talked about today apply throughout the application. Everywhere you can do any sort of coordinate system change, there's also an opportunity to do a datum transformation in those places. So lines from vectors, area features, point files, point databases in text form, raster imagery, all of these things. This applies to everything. So I think that's going to be just about all we've got time for today. So I'm just going to wrap this up. Just want to say thank you to everybody for attending. Thanks, Josie, for coming along with me here today. And we will see any of you next week for the Global Mapper session, where our next session is going to be on working with LiDAR data in Global Mapper software. And other than that, we'll be seeing you soon for a what's new in this version, as we are going to be releasing next year's version of the Geographic Calculator. Again, any follow-up questions, the email address is right there on screen, geohelp@bluemarblegeo.com. Don't be shy, and we'll talk to you soon.
Great.
Thanks very much, everybody.
Thank you.